All right, welcome folks. As people are logging in, I appreciate you taking time to join us here on your, what are we at, Wednesday afternoon? And um, yeah, going to talk today, getting into some microgrids, controls, and things like that. So again, thanks for joining in. So Ask Mayfield Anything, this is a monthly series that we do and like to put it together to talk about some of the important topics, things that are coming across our desks, and hopefully things that are of interest to you out there in the industry. And my excuse to be able to talk with really smart folks and be able to just have an hour-long conversation talking about some fun topics. So as we're going along, as usual, we love questions. And so if you have a question you'd like to ask the panel, by all means, what the request I have is use the Q&A feature in the Zoom webinar here. Things in chat tend to get lost, so the Q&A is a much better way for us to manage those questions. So as we're going along, please feel free to ask those questions, and we would be happy to try and answer as many as we possibly can. So we'll get going so we can talk about the topic at hand. And for those of you who may not know me, my name is Ryan Mayfield, founder of Mayfield Renewables, and I founded the company back in 2007. And as I mentioned, this webinar is a monthly series we've been doing for over 4 years now, and really enjoy being able to talk with folks and be able to talk about some of these topics that we have pressing for us within the industry. Mayfield Renewables, who we are. So we are a engineering company, and we provide strategic support for solar and energy storage projects and products as well. So a big part of what we do is we have really dove into energy storage systems, solar and storage systems as a whole, microgrids, and a big part of what we're doing is feasibility studies. And so that will be a little bit of what we touch on here when we kind of get into this somewhat today. But getting on the front end of these projects is a really important aspect, and being able to put some of these specific solutions into play and making sure they're planned for properly is definitely something that we take time in doing. We're also doing a lot of project engineering, so that's a big part of our business, where we are working with contractors and developers doing actual project engineering. So that's a big part of who we are day in and day out. And then there's the education and training, and that's my love, I guess you could say, part of what we're doing here today. We have other vehicles that we do. We have code corners that we put out online. We have classes that we've developed, both remote and in-person classes. So definitely would love to talk with folks if there's an opportunity to talk about some of our services with you. Okay. So I wanted to introduce, or have our guests introduce themselves. So today, getting into talking about advanced controls and microgrid savings. So first off, we have Stu Statman from Elexity, and the Chief Technology Officer, based out of Portland. And yeah, Stu, why don't you give us a little bit of background, kind of where you're at and kind of what Elexity is doing and what your day-to-day is.
Sure. So, I'm Stu Statman. I'm the CTO of Elexity. Elexity builds a CNI EMS, energy management system, that is designed to be a whole building EMS. So it manages energy storage, solar, EV chargers, and HVAC, which is one of the larger building loads sort of out there. And we manage all of that for both behind the meter use cases, primarily bill reduction and backup power management, and front of the meter kind of oriented sort of functions. So demand response, virtual power plant, stuff like that. I'm responsible for kind of the technical direction and technical implementation of the product. That's what I do.
Awesome. So yeah, so when we get into it, it's going to be interesting to talk about the product that you have and kind of the solutions that bring to it. And so it'll be interesting, and love to talk about kind of the energy management part of it, the power control part of it. And so that's definitely gonna be something we're going to jump into, and kind of how it kind of get into some of the nuts and bolts a bit. And we had some questions come up beforehand that we're talking with people, so or people sent in to us. So we'll be sure and try and capture some of those as it relates to these.
Great.
And then also we have Adarsh Ajithkumar, project manager at Winn Companies. And Adarsh, yeah, love to hear kind of about what you're doing, and then kind of as a precursor, you guys have a building right now that you're having the planning stages, the final planning stages of using this Elexity, some of the products, and being able to do some of the work that you guys are doing. So yeah, would you introduce yourself to the audience as well?
Hi everyone, Adarsh here as Ryan mentioned. So I'm working with Winn Companies, and for those who do not know Winn Companies, it's the largest multifamily affordable housing owner, developer, and manager. And we have about over 120,000 apartments across 27 states that we are managing. And we do have a lot of buildings that are very energy efficient that we are developing, but while we have those, we have many older buildings that were built in the 1970s that we are opportunistically taking the opportunity to kind of build in different energy conservation measures and improve the overall energy landscape or profile of that building. And with respect to that, we received a Department of Energy grant called Connected Communities, where we are implementing all of the different renewable energy resources like solar, battery, EV charging, and smart thermostats, etc., for overall HVAC load reductions. And we are implementing Elexity's EMS platform for optimizing the load dispatch through all of these and kind of improving the overall energy utilization as well as the dispatch strategy to reduce the overall energy usage as well as the demand charges, and at the same time enrolling in different grid service programs to kind of uh, bank more savings and get revenues that would allow us to kind of prove these strategy, which is termed as grid interactive efficient buildings by Department of Energy. So yeah, looking forward to talk about this topic. Handing it over to you, Ryan, again.
Great, thank you. So yeah, so interesting. So we will kind of a case study, if you will, of the project that Winn Companies is working on and some of the challenges around that, and that's going to be a big part of what we're talking about, as we're going through and implementing these overall topics. So kind of jump into it with that. So advanced control to bank microgrid savings, and really the thing that we're trying to address here is microgrids are complex to begin with, but as we are trying to maximize savings, as we're trying to maximize their use, both during normal grid operation, off-grid situations, there's a lot that we should be doing and we can be doing now with some of these new products that are coming on. So want to talk about that and understand how to maximize those savings and maximize the resources that people are installing, the solar resources, the energy storage, and how to properly control loads. So we have a quick poll here, just trying to get an understanding from folks, what it is, hopefully that you're looking to get out of the webinar, and make sure that we're hopefully hitting those topics. So let's jump in and talk a little bit about microgrids, set the stage. A lot of the folks on the call are probably going to be aware of this, and really just the idea with this slide and to talk for a minute or two is, what are we talking about with microgrids? What does that mean in practice? A lot of different definitions that you can come out there, but in essence, we have some sort of generation source, solar being probably one of the most common ones, but we have a generation source, and we are also utilizing some energy storage. And so in this sense of this relatively simplistic diagram, we have storage, we have a source, we have loads on site, and one of the other things is that we have is that grid isolation device. So we are able to disconnect from the grid, reconnect to the grid, operate in off-grid mode, and have all of our components talking to each other. That microgrid controller right there in kind of the center of the whole thing becomes a major part of this, and something that as part of that planning stage, understanding what that controller can and can't do, and getting it to talk to all of the different components is an important part of it. And so this is one, Stu, I'd love to kind of bring you in on this first slide even and just kind of talking about this, but we were talking about just a few minutes ago as we were wrapping up our prep on this, kind of what that controller looks like in terms of an EMS versus PCS, and what is Alexity's approach on that in order to kind of get that control going.
Sure. So our microgrid controller, we don't call it a microgrid controller because microgrid control is only part of it. We actually call ourselves an EMS, or in the context of the Winn project, we'll use a term supervisory controller. Typically, what we do is the inverter often is what's going to have the zero export functionality built into it, the sort of very high speed kind of functionality. So it'll be kind of certified to like the CRD requirements in Cal, that you'll to get on the CEC list in California. But our microgrid controller will also have baked into it what the grid requirements are, so that we don't have to rely on the PCS. So we'll have the zero grid export, or the zero battery to grid export, or the no charge battery from grid rules baked in there, and then respond very quickly, not as quickly as an inverter could, but very quickly, to make sure that those rules are followed, and typically followed within the local requirements. So the 2-second requirements in California, easily done just by the EMS. And we'll be able to do the same thing for the project that we're about to talk about in New England.
Great. So yeah, so the big, well, there's multiple functions here. There's multiple ways that we are utilizing the system, and we're going to dive deeper into this. But one is the microgrid being able to isolate from the utility, run the loads in an off-grid type mode, and then there is this ability of having the solar and the batteries and the loads all connected to the utility. And even with that, what we're going to show actually are a couple different scenarios where or different types of systems that we use the microgrids, and just we have these different scenarios we're trying to get our benefit from, and it depends on how you're using your systems day in and day out. Not to say that you don't want to think about the outage if demand charge management is all you're really after. So there's a lot that goes into it. Yeah.
That's an excellent point, and something I want to point out, something that the Elexity EMS does do to balance these two things. Unlike a lot of energy management systems, where you essentially actually block out a certain amount of the battery for like backup, you just assume that 50% of the battery is backup and everything else is economic. We actually take both grid signals and weather service signals, and we're actually able to dynamically reallocate the amount of energy sort of associated with backup power, so that we can essentially put more energy towards economic use cases where it matters, when it matters. So, for example, in Colorado, it's winter time. By default, you want a little bit more energy just sitting in your tanks for backup power, because telephone poles are vulnerable. But if a snowstorm is coming, you may want to cut your economics down to 10% or 15% or 0% of the battery. And so being able to kind of manage that intelligently, and then controlling the loads if you do go off grid, so that you can reduce the demand of the site and make your storage last longer. That's kind of part of the microgrid functionality that's inside of that EMS box.
And that's perfect. And that's where I wanted to just pull this up. And so what you were talking about is exactly what we're trying to move. Oh, I would say move away from what we're showing here on the screen in a sense. So for those of you that maybe haven't seen either this slide or this idea before, what we're looking at here is, in this case, it's a single day. It's a 24-hour period. And the black line that is holding steady in the early morning hours and then jumps up, holds relatively steady throughout the day, and then drops back down. That is our load. So that's what the building is trying to consume. The pink line that starts high at the top left and basically goes down to 0 at the bottom right, that is our battery. That's the state of charge of our battery. The yellow in the middle there is the energy that is from the solar source. The green is from the batteries. And then at the far right there, you see some red bars. And what that's indicating is that there's no source available for those. And so to Stu's point of this is a common modeling. This is a common thing that we have right now with our microgrids. In this case, this is microgrids in off-grid mode. So the solar and the battery are 100% of what the source is. And we're just going to let those let those loads run rampant all day long, and they're just going to consume what they want to consume. And so what Stu was talking about here is, well, we know that we have an outage, it's going on, and you can put kind of time blocks around it. After a 1 hour outage, I'm going to start cutting off different loads. I'm not going to let those loads turn on because I'm afraid the outage is going to go longer and longer. And you can kind of set these thresholds. So, in a lot of ways, this is what we're trying to move away from, because this is, I hate to say it, just not that there's really any dumb microgrids out there, but we're just going to let the loads do what they're trying to do, and without intervention, we're going to draw the batteries all the way down.
Yeah, I mean this is I would not call this a dumb microgrid, but
Yeah, no,
it's a classic microgrid, right?
There you go.
The goal is for the pink line to actually start at 100 because it's a high risk day. You know that it's a blizzard is coming, or you know that it's fire season. And then the other goal is that when you suddenly hit that outage moment, hey, we're just going to turn the HVAC wider. Like, we're going to make the comfort range wider for you automatically. Oh, we've gone on for another, we're down to 80%. Great. We're going to reduce the number of rooms or spaces that we're going to cool it all because we don't care about the hallways, or we don't care about the large spaces anymore. We're going to shut EV chargers down or derate EV chargers to try and get you back to when the solar comes back in and you can charge again, or to try and get you to when the power gets turned back on.
Exactly. And so, Adarsh, on the project that you all are looking at, I mean, I'm presuming this is something that you're trying to avoid, and I think that you guys have some challenges around this, right? I mean, the building's relatively old, the networking capabilities maybe aren't quite as there. You don't have the smart thermostats per se, or things like that. So, I guess, was this part of your thinking, just trying to figure out how to maximize this type of scenario, sorry for not knowing the project fully, but there is an off-grid aspect of this as well.
Yeah, so we are looking at an aspect like that, but we are terming it more as reliability or like resiliency. So
Okay.
that is basically focusing on how we can utilize the battery storage or the extra energy available to properly energize certain aspects of the building when there is an emergency. So we'll just remove or exclude a part of the panel that we want to power through the battery that would allow us to kind of ride through these sort of emergency situations. And that is something that we are still evaluating, and we'll be looking at how that can come into picture. And for Stu, that is another variable that he'll have to look at, kind of looking at the battery optimization to see if we are having a resiliency feature available within our buildings, then how to kind of optimize the battery to kind of utilize that to maximize the benefits or revenue from the utility programs, but at the same time kind of forecasting different events like emergency situations and saving some battery capacity to optimize this resiliency period that we are looking at.
That's great. Yeah. And so I think that, all of these systems, this is something that we're trying to put into play, or be able to have a better control of as a whole, for systems that we're seeing that are getting installed. The other slide that I wanted to look at, the other kind of use case, if you will, or the current microgrid control. So that last one, we were really focusing in on what was the off-grid capabilities, what is the backup type application. In this case, we're looking at something that's happening on a daily basis and doing really around demand charge management, so trying to reduce costs. And so this is one, again, I think that we can kind of roll into that same conversation. But in this case, what you see here is this is a 3-day period, and you see that battery going up and down every single day, and that's definitely on purpose. And so in this case, this specific job, resiliency was not part of the play. This was a financial play. Taking the batteries down to 0 was not a problem, because even if the grid goes out, they're not backing anything up. This is all about just making sure that we are keeping our demand charges. So in this image, the only thing that you see new in terms of colors and resource on this graph are those blue bars, that being the utility contribution to the loads. And so we see that black line still representing the loads. And what we're trying to do here is keep that blue bar so it never goes above a certain threshold. So you see that we have a certain kilowatt value there, and we're going to make sure that the batteries plus the solar plus the utility, or excuse me, the batteries plus the solar are contributing above whatever that line is. And so making sure that we have enough power in there, enough energy in the batteries is the important part here. So this is another one, Stu, I think that you guys are, looking into, and there's something we talked about in the planning, and hopefully not to steal your thunder too much on the slides that we have coming up, but things like understanding, predicting, what are the loads going to look like? How can we do some of the load shifting and things like that?
Yeah. I mean, this is a beautiful picture, but in a lot of ways it's a little too beautiful because the battery lasts for long enough to meet all of the demand. And that happens, but it doesn't always happen. And all it takes is one failure in a month. All it takes is a little bit of solar under generation because a solar panel gets, somebody throws a baseball into a solar panel, or your load is a little high unusually, and all of a sudden you don't have enough battery at the end of the day to sort of handle kind of your peak load at like 6:30, 15 minutes at a higher load, and your bill for the month will be 40% higher, right? That's demand charge management is unforgiving in that way. And so one of the things that we like about our EMS is that it's actually able to manage other loads in the system. So if we see that solar production is lower than expected, or if we see that we're using more battery than expected, we can actually manage the HVACs and lower consumption in the HVACs, cut off the spikes that the EV chargers will generate, right? EV chargers give you big square, ugly kind of load profiles. We're actually able to draw those down, and so we can stretch out the use of the battery in an afternoon to really deliver on this. The goal is not to, right? The goal is day in, day out, use sort of predictive analytics against solar production, predictive analytics against what consumption will be in the building based on weather and based on other sort of predictive magic, so that we don't have to use those things. But it's really important to recognize that predictive stuff fails, and either you build in a gigantic buffer, which is money that you're throwing out the window, or you need multiple strategies to kind of offset that demand. And so I love this picture because it shows the happy case, but I also like the pictures that show the sad ones, right?
No, and that's an excellent point of the you miss one 15-minute window out of a whole month, and you just lost it all.
Yeah.
So, you don't necessarily want to design to the razor's edge of all this, and then this is where getting better controls, getting better data is helpful because we have this ability to provide this service, but we're saying this is this is a July period. If we get a storm in July and the solar doesn't produce like that, like you were saying, this is all part of what that what we have to be up against.
Just to add to this a bit more,
Mm-hmm.
uh, so from coming from a property manager perspective, property owner perspective, most of the multifamily property owners are not pretty aware of issues like demand charge management and the utility bills that they are getting, which have very high demand charges. And to the extent possible, even without the battery, there's a lot of optimization potential within the existing HVAC systems that we have, including the smart thermostats. So, like, I know we'll be talking about this more as we move forward, but that definitely gives us like savings in terms of it's difficult to put a number on because the profile varies for different sites and different properties and including different utilities, but kind of understanding that demand charge savings are a major part of the savings that are possible with the microgrid is very essential. And I know we'll be talking about this more as we move to the HVAC reductions that or strategies that we are going to go through.
Exactly. Yes. Yeah. So with that, we can kind of maybe forge ahead and look at some of those, kind of what Elexity is doing, excuse me, and kind of as it plays specifically into your case that you guys have in Boston. So Stu, you want to kind of walk us through, I know we have a handful of slides here next, but I want to give you the opportunity to kind of talk about this, talk about the value streams and some of the ways that we can use these controls to get the value out of our systems.
Yeah, no, good. So this is basically just a recap of literally what we're talking about, but in slightly more graphic format. Like what goes into sort of understanding tariff management behind the meter and sort of what you can do sort of facing front of the meter. So DR response and VPP. Why don't we, so this is, here's an example of, a 10 a.m. thing. The forecast for the day is quite high. What we're trying to do is we know that it's going to be warm later in the day. So we're going to pre-cool zones because we know that those zones are going to get unusually warm. We're trying to carve that peak that's coming later in the day. Why don't we just go to the next slide? I think what we're going to do now is the next few slides are just going to walk through a common day. 12 a.m. to 4 a.m., if the batteries are not completely topped off, top them off from the grid, if that's allowed, right? If we're allowed to charge from the grid, it's a great time to do it because prices are going to be very low. So it's nice TOU management. Next. 4 a.m., you do sort of a predictive analysis on the day based on the weather and what you know about the building. You might do night flush at this point. I don't know how familiar you guys are with ASHRAE, ASHRAE recommendations, but often it's cooler outside than inside. And you know that it's going to be warmer later, you can flush the building with cool air from the outside, essentially economizers, and reduce your temperature, saving you money later in the day. Next.
So this is just using I mean, probably not very advanced, I would imagine. I mean, you're just comparing the outside temperature to the inside temperature, and your controls just saying, hey, bring that cool air in order to cool the building.
Yeah, exactly. There's a little bit of intelligence on knowing when to do it because there are some humidity issues that you have to worry
Okay.
about as well.
Okay.
But this is a fairly straightforward thing to do. Knowing when to do it is important, and it does depend on what the interior temperature is and what your targets for temperature are across the day. You don't,
Okay.
if it's 50 degrees out, what you don't want is you don't want to do a night flush, for example, and then make it that you actually have to turn the heaters on because it's Colorado and it's in the 50s at night and it's in the 90s during the day, and your target temperature, your comfort is 68. You don't want to be 50 degrees at 9 in the morning. You want to be 68. And so you have to be a little careful about that.
Got it. Okay.
7:30 a.m. we know that it's going to be hot in the day. We're going to do some pre-cooling to make sure that zones that we know are sensitive to that are pre-cooled, saving us later, heat later in the, sort of cooling later in the day. Next slide. High solar output, charge the batteries. In this case, we would also really crank up the EV chargers. This is a good time to use the EV chargers. And so anything that's connected, we can start doing that. This is also a good time to pre-cool. No power is cheaper than power you can keep inside the building that's generated from solar. Next slide. Cloud coverage, solar gets reduced, pause that pre-cooling, avoiding a peak. This is part of what that integration between sort of power awareness and HVAC awareness and EV charger awareness all sort of feed together. You could use your battery to avoid this peak. It's a terrible use of the battery. You'd much rather slow down your pre-cooling to be able to manage this. Next slide. Okay, this is it. It's time and it's hot out. Now is the time you really want to use the battery. If there's high EV charger use, people are setting up to go home. There's, big HVAC use. Now you're basically going to start dumping that battery. Notice we haven't used the battery earlier in the day, except for like snapping off the tops of peaks, like fast moving peaks. And so what that means is we can really reduce that evening peak really, really heavily with the battery, where a more conventional battery driven DCR algorithm would have been sort of smearing that battery across the whole day. We're actually able to snap it off and reduce the period where we do that. Next. And then buildings unoccupied, turn it back off. And look, we let the building heat up as it needs to because everybody's gone. One of the interesting things is we can actually program different zones differently. And so there could be one occupied space in this building. And so, make sure that that space is cooled, make sure the spaces around it aren't allowed to like superheat so that to make that cooling less efficient. But yeah, this is what we do. Next slide.
Yeah, so actually
Oh,
before we jump into it, we're gonna look at kind of this case study. So I'm gonna set that up, I think, a little bit with I want to talk a little bit more about the mechanics of this. And so I guess talk to me about how you're communicating with all these different systems. Like what
yeah.
does that look like? I mean, so and I think this is I'm asking the question because I know it leads into some of the complexities for Adarsh's building and the
Yep.
specific case. But in a perfect world, we just built this building, everything's in the 21st century. We have the ability to communicate, but that's not what we're coming into in most cases, I would say. So I
No,
guess,
that's
yeah,
right.
how are we communicating with all this stuff?
So again, we have to be really flexible. Like when you're getting into a building, it's a swamp, and you need to make very, very building specific decisions. But essentially, for batteries, it's typically Modbus over TCP. The EMS creates a private network. We don't want to have a Modbus interface available on a publicly accessible network, even within the building. It needs to be kind of isolated and secured. Um, the 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 EV chargers are typically Modbus TCP locally, although for ChargePoint, we can reach out to the ChargePoint cloud. For the thermostats that we're going to be using specifically for Winn create their own wireless mesh network. And then there's a gateway that we communicate to, again, um, that we communicate to through I guess in this case we'll be going back out to the cloud for them, although we could also go directly to them using BACnet, which is an old school building communications technology. It certainly is, it certainly can be a challenge to do that sort of networking. And then typically, you either communicate directly to the thermostats to manage the thermostats directly, or you can communicate to like a building automation system. And those are typically both BACnet.
So if the
Um,
building automation system doesn't exist, is this something that needs to be part of the retrofit or part of the system installation?
it depends on the kind of building. If everything is packaged units, then we can actually do all of the control through the thermostats. And so what that means is you just install um, through smart thermostats in the building, or the dumbest thermostat you can find that's got smart in the name. And then we'll communicate to those, either like we can do Modbus or sort of a custom protocol over Ethernet or Wi-Fi, or a BACnet directly to them, or even something like LoRaWAN. Um, and then you can do that. If there is a central chiller, you almost always need another piece of sort of logical software and equipment to do like chiller management. And that's actually what the Winn building is like. It's thermostats for managing like fans and valves basically, but the
Okay.
actual chiller itself we have to do integration to, and that is BACnet, and that's going to be on a private secure network kind of that the EMS has access to.
Okay. So are there any types of loads or any types of these systems that integrating with right now are proving to be difficult, if not impossible, if not just something that you're having to work on in order to be able to connect with and communicate with? Or is everything pretty well established at this point with communications?
It's pretty well established. I mean, there always are complexities, right? Like BACnet is a standard, like the English language is a standard. It doesn't actually tell you the words to say. And so there's always a certain additional set of integration tasks that you need to do if it's a thermostat you've never seen before. There are some older thermostats that are so limited in functionality that we only have like a very basic knob to turn for them. But by and large, for the best integration, for the EV charger integration, for the thermostat integration, it's pretty straightforward. For the solar integration, if we don't have to do derating on the solar, so if there's no zero export rule, we can actually just throw a meter on there. We could just meter the solar and make decisions based on that. Um,
Okay.
for the central chiller, those are sort of special beasts, but honestly, Elexity signed up for that. Like that's part of what we like special cases, because barrier to entry for other people.
Got it. Okay.
Ran, I'd like to add to that.
Hmm.
From our perspective, like looking at our own building, it being a masonry building that was built in the 1970s, there were a lot of communication challenges. For example, these buildings don't have Wi-Fi setup in by default, and that would cause so many difficulties in terms of implementing the smart thermostats. So when we were looking at the different products that are available, and we kind of quoted out the implementation price for Wi-Fi based thermostats, but it was almost too expensive that it didn't really even make sense, that even if the revenue that we are getting through these utility programs would not be enough to kind of optimize that. So eventually we were able to find a solution that is a mesh network based thermostat that we mentioned, but which is kind of communicating to itself and coming to a gateway that is what we are directly communicating to. So that was one of the challenges in terms of overall communications. Plus, we have our own cybersecurity requirements, considering this could be, a very advanced project. And if someone, we are hearing a lot of cases that if someone is able to get into any particular piece of the network, they can kind of control the overall microgrid as well as certain aspects of the grid and kind of do spoofing or different sort of threats that it can cause. So there are so many different communication issues that we had to deal with, and we eventually ended up with a solution that keeping everything local is the only way moving forward, and we're limiting the cloud to cloud communications to the least possible extent.
That's really interesting. So kind of one of the first things you said there that I wanted to just kind of follow up on. So you're saying on some of these things you're looking for components. The building's relatively old, and I promise we'll get there and we'll look at the building here. But the building's relatively old, and you have existing thermostats, you have existing systems, but upgrading them to specific smart thermostats, things like that, just weren't going to pencil out. Did I understand that right? And that you had to find alternative solutions for that, such that yes, you can have the control, but there is a financial payback on those.
Exactly. Like there is an additional investment that goes into it because we want to kind of set up these particular solutions, because once we get into this realm, our solutions are very limited because we have bunch of Wi-Fi thermostats available in the market, but mesh network based solutions that would actually be implemented and we are confident that it can communicate throughout the building and it can respond to Alexity's signal. That was pretty difficult, and it was eventually, like, we were able to find a solution that works now, but yeah,
Mhm.
there were challenges that caused
It
us
took
to
time.
believe that it is really not beneficial for us to do kind of smart thermostats.
Got it. Interesting. So that makes a lot of sense. And so it's like, um, I guess I hadn't put that into the equation of the overall economics of the system. So that's a good one to kind of hear you say. Um, so real quick before we move into the case study, there was a question I thought was interesting. Matthew was asking about how small of buildings you can go on with the Elexity system. So I'm presuming that's not size constrained, but there might be there might be a threshold there of like, it makes sense once you're doing this. You're like the office building I'm in, maybe it doesn't make sense. Have you guys come up with that, Stu? Is that something that you have an
You know,
answer for?
it's actually interesting. I saw that question and I actually typed a question to like to the other execs. It's like, have we thought about how small we go? Like we have conversations about how big we go,
Mm-hmm.
and like what's reasonable for that. But I would say that where we start to make sense is like we don't have a solution that's smaller than about 125 kW battery right now, and
Okay.
we don't have and so that is sort of the limitation on the battery side of the EMS. I would say that if you're only one thermal zone, like if you're a residence or two thermal zones, like a large house, it doesn't make sense. But I would say that once you've got like 10 zones, 5 zones, and depending on what your load profile is, it starts to make sense. But honestly, the easiest way to do this is reach out to us with like a load profile, and we can easily we have a set of internal automated tools that we can feed like utility bill data and load profiles to, and basically say, here's what would save you money. Here's how long the payback on it would be. More or less anything that's in the CNI space will work, but
Okay.
it depends on what the payback period is. But it's a great question.
Right.
It's a great question.
Yeah, I know, and I think there's probably more to it than even we're giving it credit for at the moment. So, where I sit in Oregon, where we sit in Oregon, demand charges, they're just not that much when you compare them to some of the other locations. And so, yes, we have them, and yes, gosh, wouldn't it be nice to eliminate those? But I think right along the lines of what Adarsh was saying, you're going to spend all this money on to get your system to that point, but you're never going to, if you don't spend that money wisely, you're not going to get the payback on it. So I think that there's part of that. And so,
And Ryan, I would like
yeah.
to add to that. So one thing that we came up against was like so while we are implementing this at one of our sites, we are also designing for 5 other sites, and we were also kind of trickling down and finalizing these 6 sites out of our own portfolio of so many buildings. So one of the things that we came across was like while we do have these demand charges, the key thing that we were also looking to make sense of implementing all of these solutions is the utility program incentives that would allow us to develop a viable business model.
Hmm.
So kind of looking at those was something that helped us understand. So if, as Stu mentioned in one of his statements, like it is very bad to use the battery for reducing the peak. And the idea behind that is you should be using the battery to kind of dispatch when there is demand response. The calls from the grid, it could be behind the meter, it could be front of the meter. And if you dispatch the battery optimally, that is when you are getting the most value out of the battery. And you could kind of implement these pre-cooling and preheating strategies to reduce the loads during the peak hours or mildly peakier hours that we are looking at. So that would allow us to kind of reduce the overall cost on a day-to-day basis while also getting higher revenue. So when it comes to these programs that are very different for different utilities and different states, it kind of has a say in what would be the minimum size that you can enroll in. So if you can dispatch that much amount of power or energy, only then you will be getting the incentive. So that's where you would be limited in a way.
Yeah, I
That's
mean,
great.
to that point, we've been talking about demand charge reduction pretty heavily to this point, but time of use and like actual like market provided price signals. Elexity is integrated to a number of price servers in California, and we're going to be integrated to another for this project. And so actually arbitraging kind of battery charging, battery discharge, HVAC usage, like pre-cooling and sort of more efficient modes against that price signal is also super important. Restricted by how much power can you actually shift with HVAC. You can't pre-cool a building at 9 in the morning and expect that to provide you, any benefit at 5 in the afternoon, but you can
Hmm.
move it from 9 to 11 if the building's sort of nicely insulated. You can move it from
Sure.
9 to 10 if it's not.
Sure. Sure. And one of the things I just wanted to pick up on what you said, Stu, is looking at these and being able to understand the buildings, send a load profile. For a lot of folks out on the call, that might sound like foreign language and just like I don't even know what that means. What does that look like? And so I just kind of want to point out this is something that we do day in and day out as well, talking with customers, looking at load profiles, helping set up these types of systems, looking at those and understanding what those load profiles are to be able to talk with Elexity and be able to, look at these and do the feasibility studies on those. So definitely something that I would, echo, but it's not always just the easiest thing of just emailing a file over.
Yep.
So, all right. That was all great stuff. So we've been saying that we're going to talk about this, so let's talk about this. Don't want to ignore the case study that we have. So, Adarsh, why don't you kind of set us up, talk about what the site is? I know we've already alluded to it and we've talked a little bit about it, but what is it that you're trying to accomplish? What were some of the challenges, and how is this solution? What the expectation on this solution for you?
So as I already mentioned, this is a property in Mass, and you can see the three different buildings, not the parking garage. The three different buildings are the buildings that we are looking at in terms of optimizing our energy usage and improving the overall economic dispatch, so that we can get maximize the maximum benefit from the revenue programs or utility demand response programs. So the Department of Energy has termed this as grid interactive efficient buildings. So what that means is, like, we are directly responding to grid signals based on the demand response events. So maybe we'll have a curtailment service provider or the utility themselves telling us in advance that we'll have a peak tomorrow from 4 to 8, and that is a signal that goes into Stu's system, and Stu will kind of uh, determine what is the optimal dispatch or optimal energy usage strategy. So do we have a very hot day tomorrow? So he will start pre-cooling, as we mentioned, in one of the buildings or all three of the buildings, and kind of optimize that. And on top of it, we'll have the BAS. So Stu will be using the BAS, and we have certain signals that we are sending to the BAS. One of them being the power limit. So chiller is definitely one of the biggest power utilization in our buildings. And these being very old buildings, the chillers are very old as well, like 25 years old. So by optimizing them, we'll be saving a lot of money there. And what I mean by optimizing these is kind of optimizing the flow temperature and flow rates in addition to the signals that are going to the smart thermostats. So that alone is going to give us some behind the meter load reductions, and that is going to save us a bunch of energy usage during the peak hours. But on top of it, since this is an advanced project, we'll be adding a solar on the two east and west towers. So the one building in the middle is the north tower that we are calling, and one is east and the other one is west. So the east and west will have solar, and we'll be putting in a battery storage at the north building, and it will also have about 13 EV chargers that will be sitting right next to it. We are kind of envisioning this as the energy hub that would sit right next to the North Tower and would have all of these. And it will be kind of Stu's headache to optimize all of these, because the thing is, while all of these buildings are master metered and have their own separate meters, they're still being served by a single central plant that is sitting in the north. So it is kind of a weird optimization problem that we have, because otherwise we would be directly looking at one optimization problem for all three buildings. But now it's weird that we have each of the buildings that we have to optimize, whereas all of the energy is being utilized in the north. So that creates a kind of more optimal solution that we need to look at. And that is the value function that we are going to be determining. And for determining that value function, the value streams we'll be looking at is these utility demand response programs. So we have a bunch of demand response programs in the Massachusetts area, like Connected Solutions or Clean Peak Standard, that allow us to kind of enroll in them and reduce our load behind the meter. So we don't even have to be front of the meter. So we can just reduce the load behind the meter, and they will have their own meters for MNV measurement and verification purposes, where they will be looking at asset level energy usage. So they will be looking at how much of the battery we have been using for reducing the load during the peak hours that they call for. So we'll be using, as I was mentioning, a curtailment service provider that will be integrating with Elexity's EMS and sending them a signal on these events happening. So these typically happen in summer because our buildings are more summer peaky. So from July to August, they will be getting signals about 30 to 60 events happening, and that signal would allow Elexity to kind of predict the load for the next day and see where the optimal usage metrics could be, and kind of determine, okay, uh, we have about 80% battery reserve. We can use the battery for the demand response, and we can kind of optimize the energy usage and reduce the peak or demand charges by the BAS plus the smart thermostats. So all of these combining together would kind of help us optimize the energy usage and as well as maximize the savings at the same time. And coming to some of the challenges, we have already talked about this a lot, but one of the challenges that I would like to mention is the retrofit challenges.
Mhm.
Given these buildings are pretty old, in many cases, we would like to put as much battery as possible. We would like to put as much solar as possible throughout the place and kind of, maximize the incentives that we are getting. Because if we are already putting a battery, it doesn't really harm us to go big or increase the size of the battery. The thing is, where we are limited is the size of the switch gears. So since these buildings are old, they have been loaded up with so many different electrical equipments throughout the years. We are limited to the panel availability, and we have to stick to that capability. And according to that, we have to kind of optimize. Okay, so this is the battery we can put in. We are limited in that perspective. This is the solar we can put in. We are kind of limited in that perspective, and we have to make sense of the available solar battery, and we obviously have the HVAC as much as possible and kind of determine the maximum savings in terms of reducing the demand charges as well as reducing the behind the meter load to get maximum benefits from the demand response programs. So that is kind of a gist of the project, but yeah.
So a lot of different moving parts is really what is how I'm taking that. And so, I mean, there's old electrical gear that you're kind of working within the constraints of, and then the configuration of the north tower and the east and the west tower. So all very interesting. And so I guess I'm a little curious on kind of that how to frame my question. The approach. So each of these are they're multifamily. So you have individual units maybe acting differently as well. So one person wanting it to be cooler than the other person. I guess are you getting down to that level of like looking at these, or are you looking at more of it kind of? Did you have to look at it larger on a kind of a more building basis than like even at a floor level or something like that?
It's definitely an interesting question. So, initially, just from the meter perspective, as I was mentioning, all of these buildings are master metered. So we are the utility owner, and
Mm,
we are paying the utility bills for
okay.
all of the tenants. So that is what is happening there. So in terms of optimization, uh, we have the temperature sets across the buildings, and that's what Stu was mentioning as different zones. Like we will set up different zones based on the temperatures,
Mm-hmm.
and will so as I was saying, chiller being old, it cannot really ramp up. Like we have about 465 units across the three buildings, but we cannot really just go and set a particular temperature 465 for 465 units. It would
Exactly.
be zone wise that Stu will be kind of optimizing it and building out a solution that would help us kind of react to the building's inertia. So building is not going to immediately come to a temperature. So there's going to be some inertia that we have to look into as well. So I think I'll let Stu talk on that a bit.
I mean, you covered it. It's a challenging modeling problem, and the fact that the thermal models don't align, or the thermal models don't cost with the cost models, which don't align with the meters, certainly makes this a much more challenging set of problems. Being able to manage all of that and sort of have kind of predictive work over the inertia and how we can move that and how we can move the needle and how much we can do at a given time with sort of the ability of the chiller to respond to additional loads or drop-in loads. That kind of, yes, that is very challenging. um I don't know how to, I mean, you talked about it. Yes, you are correct.
Well,
But
we're
as I said,
but
like finding a solution that is able to actually optimize all of these resources was also a big challenge. So that is a kudos to Elexity for kind of being able to optimize all of these at the same time. Because while we were looking at different solutions, we found solutions that are doing like a couple of them. For example, someone is doing solar plus battery, someone is doing solar plus battery plus EV charger, someone is doing battery and the HVAC. But like having someone who could do all of them was really critical for us. And yeah, that's where Alexity fitted in very well.
Thank you. Yeah, we really do think that you need to bring a pretty whole building view to the problem, and part of it is on the positive side of it. There are a lot of opportunities for saving money. There's a lot of opportunities um like creating a load curve that is the optimal load curve, but some of it's on the negative side as well. Every one of these systems can fail in terms of managing cost in different ways. Your battery can run out of power earlier than you think, or your solar isn't producing as much as you wanted, or turns out it was a way hotter day, or somebody spilled something and so they opened a bunch of windows, right? And all of a sudden your thermal management is completely out of whack. Being the likelihood of all of these systems kind of going south in one way or another, they're all doing it at once, is really, really unlikely. And so the more systems that you can add to that kind of management profile, the more you can backstop them with each other. Solar is underproducing. Well, I've got 4 other knobs that I can turn. Building it's a hotter day than they expected, or windows were left open, or somebody plugged in a space heater happened once. Great, I've got other knobs that I can turn rather than having a black hole that I'm just pouring energy into. I can do other smart stuff to sort of offset that. Unusual day for EV charging, awesome, I've got a battery to kind of back that up. And so it's there you need both, for both the positive case of, oh, so many opportunities, and the negative case of, oh, gigantic demand spike that is either going to affect me economically or it's going to drain my battery because I'm off grid.
Right, being able to dynamically respond to the those or not fringe, but just the unusual cases or the unexpected.
Somebody once said to me a very long time ago that black swans happen way more often than anybody really thinks. Um,
Awesome. Okay, well, we're getting to the top of the hour, so I want to make sure we kind of wrap this, kind of get to our final slides here and be able to wrap it up. I did relatively quickly, Stu, I see that there's a number of questions around inverters and PCSs, and I'm going to phrase just one question, kind of encapsulating multiple of these, I think. So I know that you all are working with CPS. I know that that's not you have it as one of the inverters you're working with. You also mentioned the CRD, so working with the 1741 CRD. So I guess I would expect that you guys are agnostic to inverters as long as they are meeting these standards, and so you're able to communicate with them properly. That's, I would think, an overall goal. It doesn't.
Yeah, our goal is to be 100% agnostic for inverters, batteries, fully integrated BESSes, thermostats, EV chargers, and solar. Like our goal is to be completely agnostic everywhere.
Yeah.
We do. So I come personally from the grid scale side of the world, and so I always have to add the caveat that, of course, we do a lot of testing before we sort of put a check next to, yes, we support that inverter, yes, we support that
Sure.
thermostat, because protocols they're squishy things sometimes, right? And
Makes sense.
so we are 100% agnostic, but and if somebody has a really interesting project that brings a new inverter in, we'd love to talk about it, right? So just yes,
Perfect.
we are
Yeah. And as we're seeing, the 1741 CRD move into a UL standard 3141. This is all going to get standardized more, but at the same time, we have to I say we like I'm doing it. You have to test and make sure things are actually going to work. Just because
yeah.
it's in the standard doesn't necessarily mean that.
I mean,
Uh,
and even within the context of a standard, sorry, just to
yeah, you
in one thing, even in the context of a standard. So just imagine something like SunSpec for
yeah.
PCS control. Oh my God, complete standard. It does everything you want. The order of operations, the sequence of things that you need to do, how, when you clear faults or don't clear faults, what faults you can clear or can't clear, all of these things they're very very sort of
Yep.
PCS dependent. And so you have to do that extra work, or you'll have a system that looks integrated, but the moment anything goes a little wrong, you discover it's not.
Right. Yep. Exactly. All right, so we threw up some key takeaways here. As per usual, we're getting close to the top of the hour, so always like to talk about the stuff and want to just kind of put this up there. We talked a lot about controlling these systems, but we need to get very practical about the buildings and how we're using them. I would like to just say, on the planning stage side, that's a big part of what we're doing. Again, we're, helping select equipment, looking at the feasibility of the entire project, the use of different components, and so all of those things. And then, yeah, the importance of the economic opportunities and, making sure that you're managing all the loads. So those are, some big key highlights of what we have. Kind of ran through that such that we can get some contact information here. So want to leave this up for just a second. If folks need to reach out to us, welcome to reach out to Mayfield. We're happy to kind of source the questions or, kind of connect the dots, if you will, if you'd like to connect with us. We do have our guests. We have Stu and Adarsh's info up here as well. And then finally, as we're hitting the top of the hour, just, Mayfield Renewables, this is something that we love to do, talking about these different codes, standards, products that are out there. So we have a lot of courses on our website. We're adding more and more all the time. So encourage you to take a look at our website, some of the courses we offer, and there might be a way for us to help, with training for you and or your team. And then finally, next month, I'm excited. We're going to have kind of an internal Ask Mayfield Anything. So we're going to have folks from our own team. We're going to get together and talk about something that is near and dear to all of us, these ESS standards. So we're going to be talking about 9540, 9540A. There's a CSA standard that's coming in. So there's a lot of different things in this. There's a lot of activity in this world. So we're going to be talking about that. So with that, thank you so much, Stu. Thank you so much, Adarsh. I appreciate you guys taking the time. I appreciate all of you in the audience taking the time. This has been a great conversation, and definitely excited to see the way that we move into using these types of systems.
Well, thank you for having us. This is a great opportunity and it's so much fun to talk about this stuff,
Absolutely. Thank you so much for having us.